So our next speaker is Giovanni Rizi. Thank you for accepting the invitation. The floor is yours.
Thank you all the organizers for inviting me here. Nice talk event for the 6 seminars. So this next semester is going to be about SymTFT theory, but also we'll talk about QFT as well. However, I'm a physicist, and I'm going to talk about QFTs from, say, a physicist perspective, or at least my perspective. The goal of my talk is to tell you how TQFTs can be useful from the perspective of a high-energy theorist. And I'm going to do so by kind of listing some examples in which some instances in quantum field theory and energy physics in which QFTs are important, and they describe some physical scenarios. So, as a brief outline for my talk, I'm going to start by telling you a bit what is a TQFT, or actually, should say better, what I mean when I talk about a TQFT. And then I'm going to deliver on what I just said, namely list some instances of physical cases in which TQFTs may appear. So I'm going to talk about how TQFTs describe the gap phase of quantum theories, and how this description fits in what we call the generalized Landau paradigm, namely how we can classify gap phases using TQFTs, how we can organize them using the relation between TQFTs and symmetries. And then I'm going to tell you a bit more about how we use in energy physics TQFTs to describe more in general the symmetries of quantum field theories. This framework which I call SYM. Now, in the final part of the talk, I'm maybe going to draw some analogies and some relations between topological field theories and possibly with some holographic parts. Okay. So, as was also, as I said in the previous talk, there is a precise definition available for TQFTs as some symmetric molecular functor. I'm not going to spend too much time on this. But let me say that in general, the way I like to think of TQFTs is a bit more vague. It allows me more freedom of freedom of thought, let's say. I'd like to think of this as TQFTs as some collection of correlation functions of possibly extended topological operators. Now, what I mean by this is that I have my theory, the quantum theory. This is supported, it takes place, if you want, takes as an input some d-dimensional magnitude. And then these TQFTs will have some operators. So operators themselves supported in general on some submanifold of my space-time. And then when I talk about correlation functions, I mean some functions that I construct out of these operators, which take as an input these supports. And they are topological in the sense that the only data which the correlation function actually depends is the topological data of these supports. Now, with this as definition, this is very useful for us, mainly if you want to study results in lower dimensions, for instance. But sometimes it can be difficult to use for more, say, physical purposes. For physical purposes, I mean directly, say, computing correlation functions and computer observables in some given TQFT. So, what we usually do in physics is to kind of switch perspective, and instead of using statistics, use action principles. Okay, so we go and use the tools we are more confident in. And here I'm going to make an example of how I think of TQFTs and how I use TQFTs, let's say. And here I'm going to talk about the example I'm going to make is this d-dimensional Zienovich theory. So I brought here a simple action. It's so the integral is over some d-dimensional manifold, and I'm integrating a top form over this manifold. But this A1 is a U1 connection, so a U1 bundle of my manifold. So instead is some higher form U1 connection, instead of having a bundle of higher J. So these are the fields of my topological quantum, and as usual, being connections, they're coupled to gauge transformations, which are given by these two parameters, lambda d minus 3, whose differentials provide me some quantized Topology classes. Okay.
What does the CN stand for?
CN is say group over the rank. Yes, yes.
How comes this formula?
Sorry?
How comes this formula? See the part at N. I can see it.
I will show it to you. Indeed, you can ask how we compute actually things using this perspective. And okay, formally, what we like to do in physics is to use path integrals. Okay, this is not really a well-defined concept, of course. We call the formal tool. And we use it to give some formal definitions of what we mean by, say, observable. So we consider some age invariant function, as is phi here, constructed out of my fields. And its expectation value is defined by this path integral. Okay. Now, in general quantum field theory, path integrals may be very hard to define. But in those simple cases, we can get some mileage out of the fact that the theory is actually very simple. So I'm going to make an example of how we actually use path integrals in these formulations. In particular, one procedure that one can follow is this one. You take your field CD minus 2, you divide it into two parts. One part is a globally defined part, so it's just a form, a D minus 2 form of my spacetime, XT. And the other part instead is so it's a discontinuous form whose differential gives me a class in HT minus 1 with integer coefficients. And I define the path integral as a sum over the possible fluxes, and then as an integral again is globally defined part. Okay. Now, for instance, if you were to consider functionals observables which only depend on U1, there are some tricks that you can do. In particular, in this case, you do the splitting of the path integral, then you use this integral over C tilde d minus 2, and you interpret this C tilde as a Lagrange multivalue that sets the connection A1 to be a flat pattern. The sum over the fluxes will put a constraint on the holomorphism of this connection to be Zn prime. So it will only allow certain values for this holomorphism. And in the end, what you get is a finite sum for the result. Okay? So in this sense, you can make sense of the path integral because this final equation is well defined. It's a finite partition functions and various observables. So as an example of operators that are interested in this theory, I'm going to consider this holomorphism of the gauge field. So UN is an operator supported on a Q gamma, in which I integrate my one form gauge field. And UFM instead is supported in codimension 2, and it's the integral of dCd minus 2. And one correlation function that you can compute is, for instance, this correlation function here, which is an example of what I was saying before. It's a correlation function which takes as an input, if you want, two submanifolds of my spacetime, gamma 1 and sigma d minus 2, and it spits out some result, in this case a very simple result, which only depends on the linking number of these two submanifolds. So in this sense, it only depends on the supports up to continuous deformations, let's say. And to answer the question before, you can also see that if you have, if you put small n or small m equal to Pn in correlation functions, these operators become trivial, so they become the identity operators. In this sense, the algebra, if you want, the algebra of Zn or a cyclic group of whatever. Okay. Okay. So, of course, this path integral perspective is not the only one that one can take. For instance, another perspective that usually taken is that doing what's called canonical compensation, so basically finding what are the hyperspaces of these theories. Can you repeat that? Sorry, repeat the last sentence. Basically, what is quantizing the theory, canonically quantizing the theory, I mean constructing the hyperspace of the theory. Okay. Hyperspace. And what you will find in this case is that you will get an hyperspace which is always finite dimensional. So it's a very nice and explicit way of constructing the space. And some advantages. An advantage of this formula is that you can easily generalize it to, instead of having, say, a one form HV and some three form HV, or some general, more general gauge fields. But a slight of a drawback is that as long as you work with abelian gauge groups or abelian groups, it works very well. But for non-abelian ones, there are some problems. Let me say that basically what I described. If you work say in D3, but this is just a diagram in theory that you construct out of Cn or back Cn. Okay. Okay. So what I want to convey with these past few slides is just one way in which I'm thinking about this is a sort of concrete approach and pragmatic in which I compute things in representation of the theory. And I'm not aiming for full generality. So now let me do the next part, in which I'll try I'll tell you some instances in which TQFTs make an appearance in high energy physics. So
Have an example of no damage.
yeah, there are examples. Since the derived zero TQFTs, general fusion categories, they don't have a Lagrange. This as far as I know. Not always. It depends a bit on the categories. I mean, there are some ways in which it might be at a Lagrangian, but it's not super. It's not always clear how to do it. Okay, so the best instance, which I think is the most natural instance, TQFTs appear in quantum field theory as a description of gap phases. Now, let me just describe a bit the framework that I have in mind. So what I'm considering is a full-fledged quantum field theory. So, one way of thinking about this is that I start some 2D conformal field theory, so a fixed point of the energy flow. I deform it by some relevant operators, and this will have an energy flow, which is just schematically denoted as arrows. And it will flow so from the UV, so you can think of it as high energy, so small distances to large distances, low energies. Okay. And the general question that we ask is, given some UV presentation of the theory, given some UV CFT and relevant deformations, what are the possible infrared phases that we can have? And generally, we want an answer that looks like this cartoon. You will have some parameters that define quantum field theories, the couplings of the silent deformations, which are parameterizing this axis. And in this parameter space, in this space, I will have some regions, ABC, which label phases. So these are infrared descriptions of my theory to which I flow to which the theory reduces in some given region of parameter space. And of course, this can be separated by some phase boundaries that can be phase transition or some more complicated points in which more than one needs. Okay. But yeah, the general idea is that I want to understand what are the possible infrared descriptions of my theories. And to do so, we make some kind of tautological distinctions between the possible cases. The first distinction I want to make is between a gapped phase and a gapped phase. So one way of thinking about this is that my quantum field theory will have an Hamiltonian. The Hamiltonian spectrum of the Hamiltonian gives me the energies of this possible states in my theory. And there are two pictures, distinct pictures. The Hamiltonian will be bounded from below, so we have a vacuum, general. And then there are two possibilities. You can either have a continuous spectrum that starts from the vacuum and goes up, or you can have a gap. So you can have the vacuum and the first excited state is some finite energy. Okay? So these are these two scenarios. Now, in the gapless case is very interesting. You can have gapless spaces, for instance, if you have spontaneous simply breaking of some continuous symmetries, but I'm not going to talk much about this. What I want to focus on is this gap space. So basically, what I'm looking at is the ground state space of some Hamiltonian. I'm looking at the properties of these ground states. Okay, these are all yes, and also here I can make a sort of tautological distinction. This Hamiltonian can be trivially gapped, and I mean that if I look at the spectrum, there will be a single ground state for every possible topology of space. Okay. Or it can be non-trivially gapped. And in this case, I can have there are many possibilities. I can have some finite number of ground states, so many states with all with zero energies. I can have what I'm going to call topological order, which is the fact that the number of ground states depends on the topology of space. Or I can have not too many situations. For instance, some fast speeds, or complicated situation. But the main message I want to give here is that whatever the situation is, as long as the theory is gapped and you're looking at the ground state of an Hamiltonian, this is the same thing as talking about QFTs. Okay? So, in this sense, classifying gapped phases and looking at what are the possible infinite phases of a quantum theory is the same as classifying the TQFTs. Now, this in general is a very difficult task if you want to do it in general, if you want to do it, say, in the most general setting. And a good idea that has proven fruitful throughout the years is to introduce more data. And the data that I want to introduce are symmetries in order to simplify this classification. So the framework is the same. Now I have always my sort of algebra flow, my quantum field theory, but now I'm adding the data of some symmetry C. Okay, this C here. I'm going to think of it as a symmetry, but in the most say modern sense. After this paper, which now is almost 12 years old. I'm going to think of it as a collection, and now I'm going to say a discrete and finite collection of topological extended operators. So these are topological in the same sense I was saying before. Namely, you insert them in correlation functions, and these correlation functions really depend on the support of the sigma phi up to continuous deformations. Or if you want, in more quantum field theory terms, you can say that they commute with the energy moment. They are extended in the sense that they are supported. They are three-dimensional submanifold like this time. And they are operators because they act on the hyperspace of the quantum theory. Okay. Now, this collection of operator C, we expect it to have some structure, just from a physical standpoint. So, in particular, what we expect to be able to do is, first of all, we expect to between these operators. Okay. Here in these pictures, I'm just drawing, if you want, a cartoon for the supports of these operators in space-time. So I just take two operators, bring them close, and then I can express the result of this fusion as some sum over operators. I expect to be able to form junctions, okay, where these operators meet in some higher two-dimensional models. And I also expect them to have an interaction with non-topology, so the rest of the quantum theory. In particular, I expect an action by linking. So if I have some dimension P operator, I expect them to act on P minus one dimension of non-topological operators by linking. Okay.
Any of those composition corresponding composition operators?
Yeah, the first one is composition of operators as an action on the hyperspace, if you want. Yes. Yes. Okay. So these structures, of course, have been studied over the years. They are clear if we have been mostly studied if we focus on lower dimensions, in particular in 1 plus 1 dimensions, based on a surface. And here, the most studied case is that of topological disequence. So I have codimensional topological operators, so polygon lines in space. And the correct structure, mathematical structure that describes them is that of fusion category. Okay, so the operators are labeled by objects by categories. Fusion coefficients NABC, they are the dimensions of some Home space in the category where they are positive integers, and these junctions are elements of the Home spaces themselves. Here I've also added a cartoon for the fact that the fusion category generally comes with more data, but it comes with an associator and so on a symbol. Okay. And I'm also going to use to introduce some terminology which is commonly used in physics. which is that of a non-invertible topological defect line, which is an object, if you want, in my category, such that if I fuse it with this dual, this fusion product does not equal the identity. Okay? It contains the identity, but it's not just identity. Okay? This is what I'm going to call a non-invertible topological defect line. We're going to do a similar discussion also in 2+1 dimensions. In this case, the natural structure is formed by surfaces and lines. Okay. And the expected mathematical structure is that of a two category. So my objects would be labeled surface variables, dimension 1, while one more things would be dimension 2 lines. And two more would be junctions of particles. Okay. But the subcase of this general structure is that of is what I get if I consider only topological line operators. Okay? I forget about the surfaces, I consider topological line operators, and in this case, C can be described as a braided fusion category. Namely, on top of my fusion category, I add an operation of braiding. So I add an R symbol, and of course, it has to satisfy conditions. And let me also introduce another piece of nomenclature that I'm introduced instead of B-form symmetries, which is just it's a name for the following situation. I have some topological operators in my theory. This will, and if they act on p-dimensional objects by linking, this form B-form symmetry. So generally, the operators of dimension d minus p minus 1. Okay. So in the case of lines, so one-dimensional operators in 2+1 dimensions, this form of one-form symmetry is the link with lines. Okay. We could go on and consider higher dimensional examples, which are higher categories. But I think it's better to return to what I was aiming at before. Maybe introduction to symmetries, which is in general program of classifying gap phases. And the idea here is that now when we look at a gap phase, what we have basically, I was saying before, is a collection of ground states of my Hamiltonian. And since I have the symmetries, this ground state will form some, will be acted upon by the symmetry that I have. Okay? And so the gap phase itself can be thought of as a particular realization of the symmetry C. Now, this is again a bit vague, but can be made more precise. For instance, again, in 1+1 dimensions, if I'm looking at different categories studying the symmetries of theory, then the possible grounds, the possible vacua get described by module categories of this fusion category C, or this fusion category C. Okay. Now, why is this useful? It is useful because it allows me to classify phases, classify gap phases on a using symmetry, so symmetry phase classification of phases, which is what one would call the first part of the Landau paradigm, in the sense that I'm now looking at distinct gap phases and I'm characterizing them using some symmetry structure. And the other advantage it does is that it provides a sort of unified perspective on all possible example phases. Some physics, but it provides a unified perspective on all kinds of phases using these generalized symmetries. So let me give some examples. We need a case of general transfers, my Hamiltonian on some on manifolds of degenerate ground states, and this is the equivalent to say that I have a spontaneously broken a discrete zero-form symmetry. So zero-form symmetry is the one generated by codimension 1 topological operators. Okay. What this discrete zero-form symmetry does is act at the vacuum, if you want, on the ground states permuting them. Okay. And here I've written two examples. The first one is one of the simplest possible ones. I consider 1+1 dimensional SymTFT deformed by the thermal operator, namely I add the temperature if you want. This temperature is an instance of one of the parameters that I got the possible phase space for. And of course, there are two phases. One in which at low temperature the system is ordered, and the T2 symmetry of the SymTFT is spontaneously broken, so you have two ground states. And this phase can be described by which just has ground states. Or if you take it at high temperature, instead the T2 symmetry will be preserved, and here is just one. Okay. And of course, these two things are exchanged by Kramer's linear. Now, the other example I've written is just is a theory of 3 + 1 dimensions, and got one strange variant. It's very similar in the sense that also here you have a path for symmetry breaking from C1 to C2, and you have n vacuum in the area. And I'm adding it just to say that these ideas are quite general. They apply to all kinds of theories, from 1 + 1 to 3 + 1. Now, let's say the vanilla case, the simplest case of spontaneously broken discrete symmetries, but we can have also more cases. This is a logical order, which for me means the same as having a spontaneously broken iron symmetry. Okay, and one simple example of this is the generalized theories, 2 + 1 dimensions. Here I've added also the word Maxwell and second theory, just because I'm adding some other non-topological piece to the Lagrangian in such a way that I have an anti-flow, but the infrared is just this Chen-Simons theory that they did there with level K. And it's known that this Chen-Simons theory, U1 level K, has K Wilson lines, Wn, and these K Wilson lines, they form, they generate what's called a CN1 fix. Sorry, it's K1 fix. What this means, it means that the Wilson lines, Wm and Wn, they braid among themselves with this phase. Okay. Yes, and in particular, the fact that if you, the consequence of this symmetry is that we have quantized certain stereo on some manifolds that we call R times sigma G, where sigma G is some Riemann surface. What you get is that the dimension of the space is, of course, depends on the quantum way of this is just taking K states by wrap my lines on the various non-contractible cycles of sigma G, and the more non-contractible cycles I have, the more states I can create. Okay? This is the hallmark of having spontaneously broken moments in a discrete quantum field. Okay? But there is another instance in which spontaneously broken one-fold symmetries play a very important role. This is, I would say, one of the most important physical contexts. Which is that of the confined or deconfined phase of 1 billion Ricci theories in T + 1 dimensions. And also here, the sharp definition of the confined or deconfined phases is through this having a preserved or spontaneously broken tendency. The canonical example also here is SUN-Yang-Mills theory. This theory has been formalized again. Now they are labeled by SUN irreducible representations, but it also has a one-fold symmetry because these lines, which acts on these lines, and the charge of these lines, if you want, under this symmetry is the anality of the irreducible representation. Now, what it means for a one-fold symmetry to be spontaneously broken? Well, you can detect it, defining, by looking at the expectation value of Wilson lines when you consider them on very large loops. Okay. Now this will decay, and there are two possibilities. One is exponential, but in the perimeter of the loop. This is called this perimeter law. And it's C. That's the spontaneous breaking of the zero. Okay. The other possible behavior that you can have is the exponential decay, but with the area of the loop. And in this case, complex symmetry is closed. Okay. Now this is related to confinement and deconfinement, just because you can extract some potential with particles from these behaviors, and the behavior responds to a linearly attractive potential. So all particles are confined, tend to be very close to each other. Okay. But this was just an example to complete this kind of identification of phases via symmetries and the relation of symmetries. It's very useful to put kind of all phases under the same umbrella, let's say. Okay. And so far, what I've talked about is how you can use TQFTs. By TQFTs, in this case, I mean phases and the relation of symmetries to classify possible phases. But actually, TQFTs are more than just a classification tool. In particular, in many cases, they help us in also studying what's happening, not just in the d-pi-r, if you want, not just in the ground state space of my Hamiltonian, but also as I move higher up in energy, so in Hamiltonian. And I'm going to motivate this with two instances. The first one will be the modified crossing in 1+1 dimension, so I'll get to it in a second, and the second one will be the construction of some effective theory for 2+1 dimensional phase transitions. So, this first instance of modified crossing was developed in a paper by Sanchloretti, Siacordo, and Ciotocomatsu 1 or 2 years ago. And the setup they consider is basically the same as I was considering before. You can take the tri-criticalizing model, which is just another name for the second safety in this unitary minimal model series after the isomorphism. You can deform it by some operator, 5 to 1, and this will trigger energy flow. Okay. A lot is known about this theory. This has been studied extensively by some dates. And yes, in particular, what would be the first thing that is done, it's in line with what I was saying before, is that it has a gap. Sorry, the first thing that is done is that along the flow, so this is given by the Fibonacci category. So yeah, two topological, one non-trivial topological line can prove this W with this fusion rule, and of course some Fibonacci. What's known is that the infrared of this theory is described by, if you want, the regular module category of the Fibonacci category, which is the only one for the Fibonacci category, and it's a gap phase with 2 okay. And thus far, this is another example, if you want, of a theory with a particular gap phase in the air, which we can interpret using symmetries. But the authors of this 2024 paper went beyond, and they wanted to study actual observables in this, in particular scattering of massive excitation. Okay. So in this case, since we have 2 vacuum, there can be, say, 2 types of excitations, which you can think, if you want, as states in the Hilbert space here. Okay. There are 2 types of excitation, which are either particles, which sit in one vacuum, or fish, which interpolate in different vacuum. Okay. And okay, without entering too much into the details, of course, a very important factor is that it's a Degree, which is a number of conservation laws, and you can compute exactly the S matrices for massive excitations, this SABC, this net FLE. They are again basically the same, taking values in the set of objects of my Fibonacci category. So it will be either 1 or W. Here is rapidly variable. And these matrices can be computed explicitly using a mixture of Buster equations and the okay. But what I want to highlight is the fact that the solution is scattering problem has this clear property of obeying modified crossing. Modified crossing. In particular, crossing would be the same equation but without the square root factor. And the presence of the infrared TQFT is what enforces the extra square factor in the modified crossing. Whereas these here are just the quantum dimension of the lines of the different spectrum, right? So, to give an instance in which, if you want, the knowledge of the infrared TQFTs is important. You need it in order to correctly compute important observable theories. So, okay, the justification of this factor of square roots, if you want, it's a bit technical, but it comes from TQFTs affecting the normalizations of asymptotic states. So you have some asymptotic states representing the path, but they are normalized according to T. And the other comment I want to make is that this is much more general than the simple example that I presented. The material integrability is not a requirement. It holds whenever you have some non-trivial integrability. Okay. I think this is an important case in which TQFTs are actually very important. Okay, so the other instance, there is some expectation that something similar holds in higher dimensions as well, particularly in 2+1 dimensions. There is some hints that there is modified crossing in Simon's matter theories, but I don't think it's as sharp as this. It's not clear what's the infrared effects that produces this modified crossing. Okay, so the other instance in which I think that TQFTs play an important role is the construction of an theory called specific phase transition in 2+1 dimensions. What I want to call Landau paradigm part 2, in the sense that the first part was just identifying the gapped phases, if you want a TQFT T and prime in this case. The part 2 is to construct an actual theory that interpolates between the two. An actual quantum field theory that interpolates between them. And in this recent paper by Cheng and Cyber came out just, I think, a couple of months ago. What they do is to consider two TQFTs T and T prime, which are the definition of ENA. Okay, so what I do here is that my TQFT T prime, they will have a category of line operators. It's a modular tensor category. And anion is just another name for the lines in this category. Okay. Now A is an abelian anion in the sense that if you take consecutive fusions of A with itself, you reach a point in which A to the n for some n, it's 1. Okay. If you want to it's generating a Zn one symmetry. And for this particular type of transitions, they were able to construct an effective theory explicitly, in the sense that they were able to write down some Lagrange. Now, I'm not going to go into my details of this, but my main point is that I want to make is that in the construction of this Lagrangian, a lot of information about TQFTs was used, in particular about the relation. The only other data that they input is this one, extra degrees of freedom, which is represented by this complex scalar phi here. But in any case, they were able to make this construction. Okay. And okay, what you can see is that depending on this sign of this parameter mu, you interpolate between the two phases. Okay. Okay. So now I'm going to.
Can I ask you something about the theories? Yes. This is the notion of gap theory. I'm assuming that T and E prime
Gapped theories, yes.
This construction is kind of a path in those two theories.
Yes, you can think of it like that. Yes, you can think that. I have my parameter mu, that number there. Okay, so this is the mu equal to 0, and I have my T and my T prime. Now this action here, if you want, is something that describes all these axes. Okay. Now So this theory that I've written here is a gap theory because it's either T or T prime, unless unless you are exactly at mu equal to 0, let's say. So it's a gap theory, but depending on the value of mu, it's either in the T or T prime phase. Okay. Mu is no, it's a real parameter. Well, mu. Sorry, mu itself, yes, can be. Yes, but I'm only going to take, if you want, these two branches, either mu squared is positive or it's negative. You could study the theory with complex mu squared in principle, but generally you lose important properties such as unitarity or. Okay, so now I'm going to the other part of my talk, in which I will still discuss TQFTs, but from a slightly different perspective, in which yeah, because as I was saying before, is what the current view of symmetries, what the way we think, the way in which we think of symmetries in quantum field theory, as I was saying, is a collection of topological operators. Okay. Now, intuitively, what this means is that every quantum field theory with some symmetry has some form of topological sector. If I just look at these operators inside the theory, okay? And the general idea is that I can use TQFTs to describe this particular sector of the theory, so to describe the symmetry of my quantum field theory. Now, why is this important? It's important because quantum field theory, one of the few angles that they have on actually studying, making predictions about them are symmetry. So these symmetries will have some kinematical consequence, such as selection rules or Toft anomalies. And this can be kind of easily understood in TQFT. Okay? So the main conclusion of this philosophy of using TQFTs to describe symmetries of quantum theories is this SymTFT construction. Now, the idea of the SymTFT is to separate in some way the dynamics, so the complicated part of the theory which we cannot generally solve, from these kinematical constraints that come from symmetries. Okay? And the way it does so is that we take as an input TQFT, so it can be, for instance, a category in 1+1 dimensions, and we run a machine which produces for us a T+1 dimensional TQFT, Z(C), which we call the SymTFT. Now, the picture that you should have in mind is spark boundary relation. So I have my physical theory, my physical boundary, which is three-dimensional, and this physical boundary is a boundary condition for my TQFT Z(C), okay, one-dimensional model. So what's the machine that constructs this TQFT? Well, okay, mathematically, some form of state some construction. Physically, the way we think of it is that we gauge the symmetry C of the boundary in one-dimensional boundary. Okay. So let me give you an example, and as the same as an input, a vision category, and then this TQFT Z(C) is the to-right zero TQFT constructed out of different categories. Now, some properties of this is that, as you probably already know very well, if we have two Morita equivalent fusion categories C and C prime, the infinite center will be the same, so the category of lines in the to-right zero TQFT is J. So in this sense, this to-right zero TQFT is an invariant of the Morita equivalence class. Now, what this physically means is that whenever we have some symmetry, we have access to what we call radical manipulations, if you want, discrete gaugings of the symmetry. And this Z(C) is an invariant of these operations. Okay? Lowest to say. The other important fact is that this Z(C), this to-right zero TQFT, has a canonical topological boundary condition, which I call BL. And this boundary condition is such that if I construct a slab, if you want this, you can think of it as a d-dimensional manifold, which is this boundary times the interval. Now, on the two ends of the I have my initial theory and this boundary condition BL. And when I compactify, this interval, I recover my original theory. So if you want, the SymTFT framework is a way of kind of blowing up the theory from t dimension to t plus 1 in a way that kind of separates the dynamics that is happening here on the boundary from the kinematic, the symmetries and the kinematics, which is instead something that takes place in the body. Okay? And the body is a TQFT.
Wrap up in 5 minutes.
Okay. Wow. Oh, no, it's fine.
Actually, number four, the example you have before, can we go back one?
Yes.
So, we start with
Yes.
perspective, that's right of 0.50. What would be the boundary in that case?
The topological boundary
Yes.
is usually you're guaranteed to have one topological boundary, at least one. It's I don't know. I'm used to think of it as some Dirichlet boundary condition for the Z of C. But I think there is a canonical mathematical construction that you can make of this boundary condition. If you want, maybe one way of thinking about it is that in the TQFT, you're guaranteed to have a Lagrangian algebra. Okay. And there is a correspondence between Lagrangian algebras and topological boundary conditions. Okay. So you're guaranteed to have at least one, and to that more. So I'm not sure what I mean by Lagrangian algebra. Okay, very roughly speaking, is some maximal set of completely transparent anyons, so completely transparent lines. But indeed, is precisely some algebra object in the Trimfeld center of the or in the Trimfeld center of C, with some adjectives like symmetric, continuous, and also Lagrangian in the sense that it's maximum. And the idea is that the R space condensation of L, so if I condense this Lagrangian algebra in R space, the resulting one category of lines in the condensed here will be the category of local modules of this Lagrangian algebra, but this is trivial. And so what you get in R space is the trivial TQFT, and this way you can construct some boundary condition for Z of C. Now, summarize this SymTFT framework. SymTFT is a way of disentangling dynamics with kinematics. You can study some topological properties like difference classes without reference too much to the dynamics. It realizes this philosophy of using TQFT tools to describe symmetries in quantum field theories, and in particular to use these tools to derive implication about the theory. And also, let me say that Z of C is in the sense universal, in the sense that the only input it takes, of course, besides the dimensionality of spacetime, is C itself. So it's something that applies to whatever theory that has the same symmetries here, which provides this abstract notion of symmetry. And yeah, so one application that has been made of this by Lea and grouping in Oxford is that, again, related to gap phases and classification of gap phases. I'm not going to go into the details because I think Lea is going to talk about this next week. But the basic idea is that you now consider the slab with two topological boundary conditions. You fix one, which fixes, if you want, the symmetries, you vary the other, and you will construct all possible QFTs or possible gap phases with that symmetry. Okay. So I think I ran out of time, so I think I'm going to stop here. That's okay?
Yeah, okay. So we have around 10 minutes of questions, interaction, and
could you flash with you as well?
Yes. Yes, okay, so what I was going to say is that it's a very old idea, it's little Witten and some old create, which in some sense you can think of TQFTs as some confined phase of gravity, in the sense that TQFTs are generally defined, they don't depend on the method of my manifold. And yeah, in some sense, they are gaps. course, there is no gravity, so it's in some ways I can find piece of gravity. So somehow you can think of TQFTs as very tall model for theories of gravity. Okay. And on top of this, sometimes when you think theories of gravity, you also want to have independence on the topology. The sum of the topologies, but here, for instance, following a paper by Francesco Benini, there is another way of getting rid of the dependence of the topology, which is to use basically trivial TQFTs. Now, before I told you that if you condense the Lagrangian algebra of the Dirichlet center in the trivial field TQFT for some SymTFT, you can construct trivial TQFTs. And so, a sort of question that you can ask is if I consider this as my theory of gravity and I put it on a manifold boundary, is there some quantum field theory that lives on the boundary of this manifold that is holographically dualities? And okay, we started this in some paper a couple of years ago, and the answer is that there is so much, okay? In the sense that you can study this for continuous symmetries, and the holographic theory will be, the dual theory will be some effective field theory for the spontaneous symmetry. Okay.
Other questions?
Again, what would be IR stay for?
Yeah, so UV, a picture that you can keep in mind, for instance, is imagine if you have some correlation functions of my operators.
It's abbreviation.
Ultraviolet, infrared. Ultraviolet and infrared. High energies and low energies. Okay.
Other questions? So if there's no other questions, we just thank again our speaker.